Result.
Yep.
Can you hear me?
Yep, I can hear you.
There you go. Is everybody else in the room?
Yes. Yes. My two supervisors and assessor. Yes.
So Fred's there,
Fred's
Dikai,
there. Yes.
Milan.
Yes. And
Yep.
Milan is here as well. Yeah.
Okay, great. Well, we're on time. Did you want to start your PowerPoint presentation so that I can just make sure that I can see it properly?
I think I've shared already. No?
Yeah, it should be on screen now, Gavin. I can see it on the screen.
It's cool.
Okay, go for it.
Is there a timer or something? No? Okay. Here it is. That's fine.
There isn't one, but I will keep time and
Okay. Okay.
probably 30, 35 minutes probably at most.
Okay. Okay. Thank you.
Will that be okay for you?
Yeah, that's fine. That's great.
Okay, go for it.
Cool. Thanks. So let me start. Welcome everyone. This is my Candidature Assessment 2. I'm in a second year of my journey on PhD. And I will be presenting my PhD thesis with the title of Improving Trustworthiness of Human-Robot Collaboration for Safety Critical Applications. And my name is Resul Dagdanov, and my supervisors are Dikai and Milan. And thank you for coming here. So let's start. So before I will introduce the research topic today, and then I will go through my Candidature Assessment 1 as a summary, and I will explain what progress I made after my Candidature Assessment 1. And then I will explain what kind of plans we have made and what kind of changes in the plan we did. So then I'll discuss some of the challenges or some uncertainties that I can face for the rest of 1.5 years of my journey. And finally, I will summarize today's presentation. So first, the research topic. As you all know, the robotics in general divides into a couple of categories. And one of the categories is the coexistence of robots. Such as if you can see that the refrigerator at home or cleaning robots, they are coexisting with us. But also there are more advanced robots such as that humans cooperate with, such as autonomous cars or a robot that you can control or robot that you hold and drag. Those robots are cooperative robots. And then while moving along to advancements in robotics, we come to the collaborative robots. And the important part here is that I want to show is that as we move towards the coexistence, cooperation, and collaboration, you all already noticed that the robot's agentic capabilities increase. But also, important thing is that the y-axis dictates on the volatility of the task. So if you go back and look at this graph and then point the high volatility task demands for collaboration. And then if you go down to the axis, and what the axis takes is that it requires some sort of agentic capability. And then trust is a foundational element of this collaboration. Because as you know, we humans do not collaborate with each other if we don't trust each other. Therefore, for effective collaboration, we need trust. We need trust to be a metric and to be used in the decision-making of the robot. And without trust, only robots can coexist, or with trust, actually transforms the cooperative robots into collaborative robots. And as we are engineers here, we care about not only increasing the accuracy of estimation of trust of a human, but also we care about how we can use this robot trust metric in robot's decision making. For example, this graph shows the perceived trust at the y-axis, is the actual trustworthiness, and you can see that if perceived trust is high, and then actual trustworthiness of the robot is low, then there is overtrust, which leads to misuse of the technology of a robot. And it has to be always, of course, dampened down. But before doing that, we need to know what is the trust value is. And I've looked at the literature, and then there are some trust management strategies. For example, if there is undertrust, we want to reduce the undertrust, then robot can do certain strategic actions, such as taking an apology or denial of an action, or control, giving back control to the user, or blaming the user, or downgrading its capabilities. Or if there is overtrust, then overtrust has to be reduced. And one of the examples is reducing the expectations, or conveying the history of performance to the user. That reduces the overtrust. Obviously, we discussed about trust, but what does really trust means in the literature is trust can be defined as an attitude that an agent will help to achieve individuals' goals in situations characterized with uncertainty and vulnerability. So the key elements here are help to achieve individual goals, which is a human's goals, and vulnerability and uncertainty of the task, in the task. So that was quite of a small, quick intro. Now I will explain the summary of my last, before CA1. So during the process of trying to identify what the trust really is, the model of trust, we came across to this better reputation system. And it is basically using better distribution and probabilistically model human trust using better distribution. The advantage of better distribution is that it has x-axis between 0 and 1, which is a good range for judging the trust. And the way better distribution works is that it relies on alpha and beta parameters. And using this better distribution in a trust model, the alpha and beta parameters can be updated while human is interacting with the robot. For example, if there is a successful interaction, then the alpha is increased, which shifts the distribution to the right. And if there is unsuccessful interaction, then the beta increases, which shifts the distribution to the left. And then there will be a lower trust in the left part of the distribution. And we took that idea and then we applied into a more fine-grained manner. For example, again, we took these alpha and beta parameters, but as I mentioned, those parameters are only updated after interaction finishes. But the question was, can we update these parameters while human is interacting with the robot instead of waiting until the interaction is finished? Especially, it's quite valuable, especially when the interaction finishes for a long horizon of time. And then we updated the beta distribution in a more fine-grained manner, meaning that instead of having discrete and binary performance metric, we have a continuous reward function that dictates how the alpha and beta parameters will be changed. And we increased the number of parameters. We added the threshold and also the epsilon value, and then the gamma to discount for memory loss. And then we optimize these parameters with maximum likelihood estimation. And we propose the framework. The framework consists of 4 stages. The first stage, human demonstrates what human wants from the robot to do. And then in the next stage, robot optimizes its decision-making policy and reward function for using these demonstrations. In the third stage, robot learns how to map the reward function that's been learned in a previous stage and to the human trust values. So human provides trust in a survey with a Likert scale with each interaction with the robot, while the reward function and a policy is fixed. And finally, in the last stage, of course, we have a model, we have a lot of parameters, we have to verify how well we are doing. So the experiment is, it's a joint task of putting the tiles into the target location from start location. And then in this configuration, robot has an end effector. X, Y, Z coordinates of the end effector are used as a robot's action. And the state vector consists of the distance to the object here, and distance to the target location, distance to the start location, all vectoral information. And as a result, we observed that our model performed better in terms of accuracy, also in fine-grained manner. But there was some limitations, such as we have a sudden change in the trust estimation during the interaction before we get to the measurement. Okay, so that was my summary of CA1.